Thanks everyone, and welcome to the CSIG-VIS International Lecture Series. So this is Siming from Fudan University. Today we're honored to invite our second speaker, Michael McGuffin, and his talk is about visual programming applied to information visualization, games, simulation, and content creation. And let me introduce Mike a bit. So Michael McGuffin is a professor at ETS, a French language engineering school in Montreal, Canada, where his students conduct research in human-computer interaction, visualization, virtual reality, and augmented reality. Before joining ETS, he did a PhD at University of Toronto, and before that, he worked as a software developer at a few companies, including Alice, Wavefront, and Discrete Logic. And in 2009, his paper at the IEEE Information Visualization Conference received an honorable mention. So let's welcome Michael McGuffin, professor.
Okay, thank you very much. I'll try to share.
I will start the sharing.
Okay, thanks.
Yeah, no, here you go.
So if I share. Okay, maybe you see my screen now. Thank you. So this talk is sort of an expanded version of a paper that we presented at AVI last year. So AVI, if you don't know, it's Advanced Visual Interfaces. It's a conference in Italy every 2 years. And the food at AVI is always really excellent. So if you want to visit Italy and have some great food, it's a good conference to go to. They have papers on visualization and graphical user interfaces and other topics. So we know computers are very powerful, and if we want to take advantage of the full flexibility of computers, we need to write programs, right? We need to specify algorithms. And I guess this, for me, this was an inspiration to me when I was a teenager, but even more than 30 years ago. It's what I guess partly convinced me to learn how to program, and probably a lot of you, or most of you, or even all of you enjoy programming too. But programming is difficult. It's difficult to learn for most people. And even expert programmers make many mistakes when they write programs. There's many details that are easy to get wrong when we're writing a program. So if we could find ways to make programming easier, maybe more people could leverage the power of computing, and maybe this could unlock more potential of computing and even unlock more potential of humanity. Okay, so this is an inspiring vision to me. So how do we do this? How do we make programming easier? Well, one way is to just solve the problem of artificial general intelligence. If we can do that, if we have computers that are as smart as a graduate student, we could just tell our computers conversationally what we want them to do. And then problem solved, the humans don't need to write programs anymore. But this problem is difficult, and maybe no one person or even no one team can solve this problem. I remember Marvin Minsky talking about, if you take a book about the anatomy of the brain and you look in the index, you can find a list of hundreds of different parts of the brain. So maybe there's many hundreds of little machines in the brain, and to make a computer as intelligent as a human, maybe there are hundreds of different subsystems that need to be developed. So it could take decades to do this. So a different strategy, which is maybe less ambitious, is maybe there are ways we can make programming easier by making it more visual. And of course, this has been a research topic for decades. Many people have worked on visual programming and related systems. And I'm not an expert on visual programming, but it's something I've been thinking about for the past few years. And I want to share some ideas with you, and also talk about some future directions. So in particular, I'm going to be interested in better understanding the limits of visual programming. What are the limitations of it? Why are those limitations there? And are there ways that we can get around those limitations, remove the limitations, or circumvent them? Okay, so here's a simple example of visual programming on the right. So this is made with a system called Blockly. I think Blockly is a JavaScript library that allows you to have a front-end interface that looks like this. So there's a little piece of code that is defined by these blocks, and it's essentially the same thing as the code I put on the left here in C#, right? So we have a loop, a while loop here, and it calculates the squares of some integers from 1 to 10 and then prints out the result. So maybe you'll agree with me that these two things are isomorphic in some sense. They define exactly the same thing. So why would we want to have this type of visual programming? What are the advantages of this? Here's another example of some visual programming. This is part of a screenshot of Scratch. Maybe you've heard of Scratch. It's often used for teaching programming to beginner programmers. And in Scratch, you have these blocks that you can drag together. They look like puzzle pieces. And you also have a menu of different types of blocks, different types of instructions. So some of them might be for changing what we see on the screen. Some of them are for creating sounds. Some of them are for controlling the execution of instructions, so loops and things like this. So again, what are the advantages of this type of visual programming? Well, one is that a system like this with a menu makes the instructions visible. It makes the set of possible instructions visible. So as a beginner, you might not know what instruction you need to do something, but you could explore this menu and maybe you'll recognize what you're looking for. So that is often a good thing for beginners. And so we could describe this as visible affordances, right? The concept of an affordance is something that was maybe first discussed in Don Norman's book about interfaces. And this is also related to the idea of recognition rather than recall. So an expert programmer might remember the name of a function to use or the name of an instruction, but a beginner might be more comfortable recognizing it when they see it in a list of possibilities and then making use of it. So, and this, I believe this is one of the heuristics of Jacob Nielsen in his 10 or 11 heuristics for heuristic evaluation. So another advantage maybe of this approach to visual programming is we have these sort of puzzle pieces that we can drag together, and this creates a metaphor, right? It looks like a physical puzzle, and the shapes of the pieces indicate to us how they fit together. And we can also think of the shapes as establishing constraints on how things go together. And constraints are another concept that's been discussed by Donald Norman and by others. Constraints are useful because they eliminate errors and they can simplify interaction. They can make it easier for a user to understand what to do. So maybe this type of approach is good for beginners, but maybe experts don't need this. Maybe this would just be bad for experts, because experts, often they can remember what they want to type. And typing is very fast for an expert typist. Also, if we were to display these instructions in text, or display the, if you take a look at this, for example, when we display instructions in text, it takes up less space on the screen than using blocks. If we compare the size of these two things, they look similar, but actually the text here is bigger than the text here. And if we were to shrink the font so it's the same size as that, this entire block would take less screen space. There's extra screen space here being used by the lines between the blocks. Okay, so maybe for an expert, this is not a good approach. It's better just allowing an expert to use text. Another question we could ask is that these types of visual programming languages I just showed you, are they Turing complete? That is to say, do they allow us to describe any algorithm? And there are some related questions to this, like maybe we might ask, do these visual programming languages place limits on what we can express as a programmer? We might also ask the question, can they be used for general purpose programming? And all three of these questions sound very similar. We could think of them as one question, but I'd like to think of them as three different questions and answer each one individually. So let's look at the first question about Turing completeness. What is it that makes a language Turing complete? What is it that allows us to define any algorithm in a language? Well, if it's an imperative programming language, we want two things in particular. We want the ability to define conditional branching. So if we can define a while loop, that's sufficient. And we also want the ability to access any amount of memory that we want at runtime. So if we have something like an array that can be resized dynamically, that's enough for Turing completeness, okay? Second question is about expressiveness. So does the visual programming language place limits on our expressiveness as a programmer? And I would like to interpret that in terms of the syntax. What is it in the syntax of the language that makes it easier to express ideas? So it's really useful if we can define subroutines in the language, right? And in fact, Scratch does have supports for subroutines, and it's not too hard to add support for something like that in a visual programming language like the types I just showed you. It's really useful if we have different data types. So it's not necessary for Turing completeness, but it's really useful if we have a distinction between numbers and strings, and maybe even Boolean types and other types. It's really useful if we can write comments, and there's other syntactic tools that we could think of. For example, the ability to define objects or classes. Now, as it happens, I don't know of any visual programming languages that allow the definition of objects, but there are ways that that could be added to the syntax, and we could add more of these things and make the language more and more expressive. The third question was, can the language be used for general purpose programming? And I see that as a question about the API that's available, the set of libraries or routines that are available to us. Do we have ways of displaying visual output? Do we have ways of reacting to input from a keyboard or a mouse? Do we have ways of doing input or output with the file system or the network and so on? All of these things are pretty easy to add to any language once the syntax has been defined, okay? So the programming languages I showed you, the visual programming languages I showed you, are easily made Turing complete. And I'd even like to use a new term, which we proposed in our paper last year. The term is GUI complete. So GUI, of course, is graphical user interface. I'm going to say the language is GUI complete if the language allows us to program any GUI that we can imagine. So any GUI that will respond with any computable visual feedback in response to any sequence of events, okay? So the languages I showed, it's pretty easy to make them GUI complete. So there doesn't appear to be any fundamental limitations in what they can do. Here's another example of a visual programming language that might look very different. So in this language, we have this diagram. It looks like a tree. In fact, it is a tree in this example. And imagine there's information flowing between the nodes and making their way up to here. And maybe this is some final result of some calculation, okay? So this looks like a tree structure. It looks like what we might call a data flow diagram. And we might ask, is this type of language Turing complete? Is it GUI complete? So take a moment to look at this in detail. I'm going to shrink down my example, and then I'm going to show the piece of code that I had earlier in an earlier slide and show you that each of the nodes along the top here corresponds to a line of code in this example, okay? So the nodes along the top here are connected by white edges, and they're little triangles. So these edges are different from the other edges in the diagram. And the way to think of this is the control of execution is passing from this block to that block and then to that one and so on. So these are executed sequentially. Here what's happening is there's a value being assigned to some variable, and then we enter a while loop. So this block is going to repeatedly execute this block so long as some Boolean condition is true, okay? And once that Boolean condition is no longer true, it's going to stop. Just like in the example code here, it just stops. There's nothing that happens after that. But if we wanted something to happen after that, we could have another white arrow coming out of this and leading to another block. So we actually have a loop in this diagram. So again, these 5 blocks along the top are special because they get executed sequentially and they can include loops. But the other blocks are different. The other blocks really are like data flow subtrees. So the data is being fed through these operations and then serves as input into the blocks along the top. And the different colors of edges we have here are, let's see, there's purple for Boolean, there's blue for numeric, and I think green is for sort of generic type. But the white edges are really different. That's why they have triangles, okay? So to answer the questions I asked earlier, this is not simply a data flow diagram because it's a sort of mix of data flow and sequential execution. And in fact, this language is Turing complete because we can have while loops, we can have if statements, we can have arrays that are changing size dynamically. So when I learned about this, this was a kind of a surprise to me. I wasn't aware that these types of diagrams could be made, that these diagrams can express Turing complete algorithms. There's a different way that we can redraw this diagram, and that makes it kind of confusing the first time that I saw this type of program. We can take the algorithm at the top and redraw it the way we see in the bottom. So what's happened here is some of the nodes up here have been merged into single nodes. So for example, here we have like 4 or 5 nodes. I guess there's 5 nodes that are reading the value of j. All of those are merged into a single node here. There's another 2 nodes here that are multiplying a and b, and they've been merged into a single node that has 2 outputs, okay? So this merging of nodes allows us to save space. In fact, we could compare the 2 ways of drawing the diagram. The version on the top has the advantage that some of the edges are shorter, right? For example, look at the edge that's here. This is quite a long edge. In a more complicated algorithm, I might have many long edges, and that leads to crossing of edges that can be confusing. But up here, because I've allowed myself to duplicate all the nodes, I can place each node very close to its neighbor, and then the edges are shorter. So shorter edges, less crossing of edges. But on the other hand, the diagram at the bottom has other advantages. We have a smaller number of nodes, a smaller number of edges. And also, sometimes we don't need to give a name to a variable that's being used temporarily. For example, here, I'm computing the product of A and B, and then that product is being used in 2 different places, right? If I wanted to do that in a textual language, I'd have to give that output a temporary variable name. But here I don't have to do that because I can just draw edges. Another thing I found interesting to notice here is there's a sort of duality. If you look at the white triangles we can think of as control flow, and the other edges are serving for data flow. So look at these triangles again. Whenever we have a triangle, we can have many edges coming in, but only one going out. Okay, we can have many edges coming into a white triangle because many statements could have the same subsequent statements. But when we're leaving a white triangle, there's only one node we can go to because the model here is of single-threaded execution. There's no notion of forking. So that's why I wrote that the control is many in, one out. But when it comes to data flow, we have the opposite situation. So from one piece of data, I can have many outputs, many copies of the same data. On the other hand, to the input of one data, I can only have one edge coming in. So there's this sort of interesting duality. Now I see someone's written something in the chat. Okay, there's a question mark. Would anyone like to ask a question? Can everyone hear me all right?
Yeah, everything's fine.
Okay. So in textual programming, we're used to being able to add comments and define subroutines. We can do that also in this system. This system is called Bolt. It's a system for Unity, and there are ways to add comments and define sort of meta nodes or subroutines. And so this language can be made GUI complete. All right, so there's no limitation in theory. There's no limitation on the expressiveness of this language or what we can use it for. So I've shown you a few examples of these visual programming languages. There is Scratch, Blockly, and Bolt. They're GUI complete, or at least they can be made GUI complete quite easily. And maybe we could say that they're mainly of interest for beginner programmers. Maybe experts would prefer to write text. Now I'm going to show you some other examples that hopefully are more interesting. These other examples are other ways of making programming more visual. And they could be useful to even to expert programmers, not just beginner programmers. But as we're going to see, they are not GUI complete. They're not Turing complete. And it's interesting to understand why. So here's the first example. This is a prototype that was made by Brett Victor. So Brett Victor is not sort of usual academic researcher. He doesn't have a job at a university. He spent some time working at Apple. I think he has a master's degree, but not a PhD. So he spent some time working at Apple doing design work for them. And then for a few years, I think he was sort of unemployed. and he made several very beautiful and interesting demonstrations of interfaces, and he went around presenting these at conferences. And anyways, this is one of the systems he made. So this system allows someone to draw a visualization and then have the visualization updated automatically if we feed in new data. So I've taken a video of him demonstrating it, and I've edited the video and accelerated it to show the main ideas of the system. So the user can draw things like draw a rectangle. They can drag and drop parts of a data set into instructions that we see at the top here. And as the user is manipulating the content here, there are instructions that are being generated on the left. There's a list of instructions here. The user can select some of those instructions and put them inside a loop so that they get applied to all of the columns of a data set. And so what they drew, the circle they drew earlier, gets repeated over and over for each of the columns. And the user can change the color or other attributes of things that they've drawn. So through this sort of direct manipulation of the content here and drag and drop operations, these instructions get updated and they get re-executed on the data set that's over here. And the user in this way can define things like a scatter plot, a bar chart, a pie chart, or this sort of exotic visualization that doesn't really have any name. It's just something that Brett imagined. And so Brett Victor does a very good job of, I think, presenting the vision of what we should be aiming for in some of the tools that we make, that we should allow a user to work within the visual domain if the type of output they want is visual, right? If someone imagines a new type of visualization that they want, they should be able to just draw it and not have to think in terms of lines of code. So another system I'd like to show you is this one. This is called Sketch and Sketch. So maybe the first paper on this was somewhere around 2016 or so, but there are subsequent versions of it that have been published more recently. And in Sketch and Sketch, you have code on the left, which is written in some type of simple language. And this code tells the system to draw some shapes on the right half of the interface. So as the user updates the code, whenever they want to redraw or re-execute the code, they press the run button. And what's very interesting in this system is the user can also directly manipulate the output, and that causes the instructions to be updated automatically. So if we change the code, the output changes. If we change the output through direct manipulation, the code changes. And there's this bi-directional relationship, bi-directional updating between the two. So again, I've taken a video of, I think it's Ravi Cha demonstrating this system, and I've edited the video and accelerated it so that you can see some of the essential features. So here the user is editing code on the left, and every time they press the run button over here, the output gets updated. So this is just some code to draw some lines, and then it's put inside a loop, so many lines will get drawn. That's what we're going to see very soon. The programmer is defining a loop to draw a set of spokes, so a set of radial lines, and now the user has drawn this rectangle directly, and some code got inserted by the system to draw the rectangle. Next, the user can change the position of the rectangle. The parameters here get updated automatically. The user can resize the rectangle, change the color of things, and again, the parameters here get updated automatically. Next, the user draws some lines inside the box and wants to constrain the lines so that the positions of the endpoints coincide with the corners of the box. What the user is doing is drawing a logo that looks a little bit like the letter lambda from the Greek alphabet. So the user is going to select different parts of different graphical elements, like the endpoint of one line in the corner of a square, and then say, make these things equal, make them have the same position. And the code gets refactored automatically. There are variables that get introduced in the code so that the selected elements always have the same position, the same color, and so on. So I think this is an exciting vision for how programming might be done, where the user always has the choice of changing the source code or changing the output, and the other side of things gets updated automatically. Later on in this video, Ravi even shows how we can take the entire thing that he's drawn, this lambda inside a square, and he can make it into a subroutine. So the subroutine gets refactored automatically, and then he can cause that subroutine to be called repeatedly by using direct manipulation on the canvas on the right. So maybe we're going to see that soon. Okay, repeat around. That's where these widgets show up, and then by changing the sliders on these widgets, he can cause a different number of instances of that shape to be drawn. Right, and inside the code, there's a subroutine that's been refactored automatically to draw this shape over and over. So the two examples I just showed you, they are not normally referred to as visual programming. In fact, Brett Victor, I think he calls this system an example of programming by demonstration or programming by example. And there's a history of many papers proposing different ways of doing programming by example. This more recent system, the authors in one of their papers describe this as output-directed programming. And it's different from the kind of visual programming that I showed earlier, because in these systems, which are usually called visual programming, in these systems, there's a direct relationship between the graphical elements and the lines of code. So the visual part here is showing us more or less directly what the lines of code are, what the individual instructions are. Whereas with programming by example or output-directed programming, the relationship is not so direct between the visual part and the instructions. So I'd like to come back to the example of Scratch. Earlier I showed you Scratch. I showed you the instruction blocks here that look like puzzle pieces, and also the menu of different types of instructions. But I didn't show you the entire interface. There's another part to the interface of Scratch which shows the output of a program. And Scratch is designed for children and beginner programmers. So in this output portion, there's a metaphor of a theater, a type of stage on which we have characters. We can have one or several characters. The characters can have different costumes, and there are instructions that allow the programmer, the child, for example, to change the costume on a character. We can also have blocks of instructions be executed when some event happens, like if two characters collide, or if the user clicks on one of the characters, we can have some instructions executed. So this allows a child to create an interactive story or even create games. Okay, and I wanted to show you a more complete picture of this interface, because now I'm going to compare Scratch with the other two systems I showed earlier. So Brett Victor's system that allows us to draw a visualization, and Sketch and Sketch, where we have this bi-directional updating, where we can edit the output or the instructions, and the other side is going to be updated automatically. So I saw these systems, and I've seen other systems where there's some type of visual programming going on. And I found these systems very interesting, very exciting, but I was also confused because it was unclear to me what the limitations of these systems are, which of them could be used for general purpose programming, whether they could be used for general purpose programming, and if not, why is that? Is there some way we can get around that limitation? And so this confusion has it remained with me for many years, actually. And maybe some of you might find it interesting that in my opinion, when we experience this type of confusion about any topic, it is an opportunity. Okay, if you're confused about how to understand something or how to think about something, it's an opportunity for you to think more deeply about it and arrive at maybe some deeper understanding. And if you can do that, then at the very least, you will have learned something. In some cases, you might be the first person to have understood something in a new way. And then maybe you can write a paper about it, or maybe it gives you an idea for a new research project. So if there are any maybe junior researchers in the audience, this might be something to keep in mind. If you're confused by something, and if other people cannot explain it properly to you, that's an opportunity for you. So what I noticed in these systems, maybe this observation is going to appear very simple, but to me it was kind of a revelation. These three systems can be cut up into two pieces each. And on the left, we have instructions. On the right, we have something else. We have something like the output of the system. So maybe we could call these things the output, or maybe there's other words we could use to describe the things on the right. I decided to call the pieces on the right the content, but there are other words that people have used to describe these things. They could be described as output, or in some cases, maybe a document, or maybe assets or resources. And in fact, there are integrated development environments that have a concept of resources or assets. And those might be very similar to these types of things. So they might have a graphical representation that can be directly manipulated. And maybe in the instructions, we can somehow import an asset, import a resource, and then use it somehow. Okay. And this type of dichotomy is actually quite natural and maybe even obvious from a certain point of view. Whenever we have code, we have the instructions, which are kind of like the verbs, and then the content or the data, that's kind of like the nouns, the things that are being operated on. So once we take this perspective, that we take these systems and we divide them up into these two pieces, well, we can notice that other systems also have this dichotomy. Like in a web page, we might have some JavaScript that operates on parts of the HTML document, the document object model, and maybe the document was created with a visual tool, like something like Dreamweaver, or there are other visual tools that allow us to directly manipulate a web page. And the code allows us to do other things, allows us to change the content. For example, in this example, the code is drawing a bunch of lines on top of a canvas, okay? Another example for those familiar with the Unity, in Unity, there's often two ways to do things. We can directly manipulate 3D or 2D content to move things around, to change their size, change their colors, etc. But we can also write code. Often we can write code that does the exact same thing. And often we have the choice of doing it one way or another. So if I take the five systems I've shown you, and I divide them up into instructions and content, then we could ask some questions about each of these examples. We could ask, is the content something that's static, or is it something that's dynamic and interactive? All right. And so in the case of Scratch, well, we can program interactive games, interactive stories. We can do the same thing with JavaScript or C#, of course. However, with Brett Victor's system, after we've drawn the visualization gets generated and it is static. Of course, we can feed in a new data set and the viz gets updated, but the viz itself is not interactive. With Sketch and Sketch, the graphical output is also static. So that's why I've put check marks in this column for these two systems. Some other questions we might ask are, is there a concept of bidirectional updating? And yes, there is in the case of Sketch and Sketch, and even in Brett Victor's system. In Brett Victor's system, we cannot freely edit the instructions, but we can change certain parameters of the instructions, and that will cause the viz to be updated. And we can also, of course, draw on the canvas that causes instructions to be changed or generated. So is the system Turing complete? Well, almost all of these are Turing complete except for Brett Victor's, because in his instruction set, there's no conditional branching. There's no concept of variable length arrays, but maybe we could add those if we want to. Is the system GUI complete? Well, for GUI completeness, you need not just Turing completeness, you also need to be able to react to input events, and Sketch and Sketch doesn't do that, okay? So this is an example of how we might start to analyze and compare these different systems and better understand the limitations of them. And then we might take a step back and ask, is it possible to make a system that has all of the properties that we want? For example, could we imagine a system that has both bidirectional updating and is GUI complete? I don't think I know of any example system that has those two properties, but I can imagine how we might build one. Okay, so given this perspective of this dichotomy between content and instructions, with my co-author, we invented a little sort of notation to summarize different systems. And so take these two examples. We have Scratch and Sketch. We can ask three questions. The first question is, how does the user interact with the content? And in both of these examples, they use direct manipulation. What do I mean by direct manipulation? Well, usually it means the user's using their mouse or some other input device with continuous input, and they can move a cursor or move a pointer continuously to invoke actions on some content. And as they do this, they have continuously updated feedback. They can also reverse what they're doing simply by reversing the motion of their arm or their hand. Okay, so this is a way we could define direct manipulation. Direct manipulation is when you have data that's continuously represented with continuously updated visual feedback, and you can undo your actions simply by bringing your hand back to the starting point. What about the instructions? So the second question is, how does the user interact with the instructions? Well, in the case of Scratch, the user is dragging those around with the mouse, so direct manipulation. But in the case of Sketch and Sketch, they are typing in instructions. So I put a T for textual input, okay? Now I'm going to take these two letters in red, I'm going to move them to the right side of my instructions like this. And that gives me room in the middle here for a third question. The third question is, how are the content and instructions related? Does one update the other? Well, in both of these systems, the instructions have an effect on the content. So the instructions can change the content in both of these systems. And in Sketch and Sketch, there's an additional relationship that is that if we change the content, the instructions get updated. Okay, so I'm going to show that with a double-headed arrow here. And now we have these little formulas that summarize these two systems. Okay, so then what we did in our paper last year is we thought about all the different variations of systems and formulas, and we came up with this taxonomy. So depending on what type of system you have, depending on the answers to those three questions, how does the user interact with the content? How does the user interact with instructions? And how are content and instructions related? We end up with all these different formulas and these different subsets of systems. So this is a taxonomy. And I won't go through the entire taxonomy. If you'd like to see me going through every part of the taxonomy, you can watch the video of me doing that or look at our API paper. But I will show a few examples of systems that we find in this taxonomy, just to try to convince you that this taxonomy does cover a large set of systems that allow for programming in a visual way or allow for the creation of content in a visual way. I have a few examples involving visualization of data, so maybe those could be more interesting to the audience. So let's look at a few. So some systems make use of pen inputs, and this particular system is for creating simulations, so physical simulations, maybe in the context of a classroom if you want to teach physics. So you can draw a simple physical system. There's a way of defining wheels and gravity, and you can hit run, and the system will interpret what you've drawn and then maybe simulate a car that's rolling down a hill. Okay. Another system that uses pen input is this one, where not only can you draw a picture, but you can draw an animation. So you can draw some bubbles and then draw an animation path, and the system will animate the bubbles following the animation path that you've drawn. So this is interesting because you can create animations just using a pen. Another example system, this one is for visualizing data. So the idea here is that the user wants to create sort of non-conventional creative visualizations of data. And in this case, it's with a bunch of flowers, so they can draw flowers and draw pathways along which the flowers get repeated. And the number of flowers or the colors of flowers correspond to some data set, again, using pen input for everything. So why is pen input interesting or useful? Well, one reason is that it can better make use of the abilities of the human hand. The fine motor control in the human hand can be leveraged with a pen in a way that a mouse cannot. Using a pen can also encourage more creativity, a more informal way of working. So there's actually a substantial literature on using pen input for doing various things. All three of these systems that I've shown you involve the user directly manipulating content, and there's no concept of instructions in these systems, right? So in our taxonomy, I would place those three systems in this subset, where direct manipulation is acting on content and there's no concept of instructions. Here are some other example systems. So this one is a game that can be programmed in a sort of visual way. This is by some Japanese researchers. The game is called Viscit. And so it works using substitution rules. So the user can draw a scene in which the game will take place. The user can draw characters, and the user can draw substitution rules that say, for example, if my finger touches the position to the left of the person, then replace these two cells with these two cells so the person moves to the left. If I touch below the person, then move the person down. So then once these rules are defined, the user can run the game, and then by touching in these squares, they can cause the person to move around in this little maze. So you could think of this as programming, because these substitution rules are kind of like instructions, but it's not Turing complete. There's no way of defining conditional branching or loops. So the formula that I use to summarize this type of system is this. The user can directly manipulate content by drawing things, drawing characters and so on. And there's also a kind of concept of instructions, but the instructions are sort of implicit. They are implied by what we've drawn here in these rules. We have no direct access to the instructions. We cannot type instructions or do drag and drop operations on the instructions like we could in Scratch. So this system is not Turing complete, right? Other examples of systems that also have this same formula, these ones are related to visualization. So Brad Myers and his colleagues have done lots of research in the past on visual programming and programming by example, and they developed maybe the first system for visualization of data that uses programming by example. And I think this system is not well known, but it's about, what is this, 25 years old or something. So the user could directly manipulate the components of a chart, and the system would update the heights and colors of bars according to some data set. Another example, this is much more recent. Here we have a scatter plot, and the user can directly manipulate various things within it. For example, if they move part of the scatter plot, move one of the dots, and if they start stacking dots together, that is a hint to the system that we want all the dots to be stacked, and so the system can infer that we want a bar chart. Or if we start changing the colors of dots according to some data attribute, the system might then infer that all of the dots should be colored according to those attributes. If we start changing the size of things, the system might infer that size should be mapped to some data attribute. And in both of these examples, one thing to notice is that the visualization that we generate is not interactive, right? There's more recent work from just last year, which is exciting because here the user is using direct manipulation to define the visualization, and it is interactive. The final result is interactive. So maybe towards the end of the talk, if people are curious, we can watch part of this video together and see examples of the interactions that the user makes to define these interactions. But nevertheless, all of these systems I've shown in the past 3 slides, they're all summarized with this formula. So there is, I would say there is a concept of instructions, but the instructions are implicit. The user has no direct access to them. And the language is not Turing complete because there's no way to define things like conditional branching. Okay, so even this system, even though we can define an interactive visualization, it's still not Turing complete. It still doesn't give us the full expressiveness of some other languages. So those systems I just showed you, I would place in this box, and we could call them programming by example or programming by demonstration. Okay, some other examples. So this example is kind of similar to Scratch because we have a visual programming system for the instructions, and instead of having a 2-dimensional theater or scene, we have something that's 3D, and we can also directly manipulate the content in the 3D scene. In fact, this game is available, I think it's available for free on Steam, and it can run, I think it can run in VR or on desktop. It's interesting to just play with to see how flexible it is. So to summarize this system, I would use this formula here. We directly manipulate the content. This is the content. We can also directly manipulate the instructions, and the instructions can act on the content. Right, so this formula we find in the taxonomy over here. Some other examples of systems that I would also place in the same category would be, oh no, I'm sorry, these are a different category. So earlier I showed you Brett Victor's system where we can draw visualization. This is different in the sense that as we draw the content, the instructions get updated, right? And the instructions also have an effect on the content. So we have a two-headed arrow here. We have the same thing here. It's bidirectional. And another example system I found, which is bidirectional, this is not published in the academic literature, but it's a product that can be downloaded. It's a product where we can visually construct a GUI that causes instructions to be generated. And if we change the instructions, the GUI also gets updated. So there's, again, a concept of bidirectional updating in this product. So these systems, I would summarize with this formula with the bidirectional arrow, and they would go in this category of the taxonomy, okay? One more example. This example is interesting for a few reasons. First of all, it's quite old. It's, I guess, 24 years old. It's also interesting because it doesn't involve two, but three different representations of the instructions. So we have a textual representation of the instructions, and then we have two different views of the content, I guess. In this view, we can directly manipulate the output, and this is a sort of iconic representation of the same thing. Another reason I found this paper interesting is it has some very interesting statements in the text. It says, for example, no single programming paradigm is ideal for everyone, for all uses. And this is a very important idea that in some contexts, a particular representation might be better for a particular person, but there's no one perfect way of allowing someone to program. And I think it's important that I think it's interesting to think about systems that allow us to switch between different representations. And instead of trying to come up with one perfect representation, give the user lots of different choices, allow them to switch freely between representations, or even maybe mix different representations together. Maybe that could be a way of unlocking the advantages of all the different representations. There's even been work done on visual representations of abstract data structures. So this is a type of tree data structure that can be directly manipulated, but there's no access to the instructions. The instructions are implied. And here's another example where we can directly manipulate the contents of an array, and it causes instructions to be implied. And another example, this I think is not even published academically. It's a YouTube video, but we can manipulate a tree here, and the instructions get generated automatically. Okay, so here are some ideas for future directions. I think one thing to think about in the future is maybe instead of deciding that a user should use text or should use visual programming, maybe we give them the choice. So imagine a system where we can freely switch between visual programming or textual input. In fact, there are systems already that allow the user to do that. And maybe more interesting, this I've never seen before, maybe we can think of ways of coming up with hybrid mixtures of text and visual elements like data flow diagrams and so on. So imagine, let's see, maybe I didn't quite finish that particular slide. Oh, here it is. I put that on the wrong slide. Can I move this? Here we go. So can we think of ways of mixing these two things together, right? So imagine if some parts of the code were shown in text and other parts were shown as blocks. Or maybe what would be more interesting is if we had a representation like this, where some parts of the algorithm are shown as text, and that text block can have edges coming out of it and edges going into it. That might allow us to mix together the advantages of both representations. The text would be more compact, maybe easier to edit for an expert, whereas the parts shown using edges might allow us to avoid defining temporary variables and be easier for a beginner programmer to connect things together that are written by an expert. Okay, so that type of hybrid mixing might be something interesting to do in future research, and I've never seen that done in previous work. So those are future directions 1 and 2. Future direction number 3, I think one particular visual representation of instructions that might be very useful is finite state machine. There's lots of code written for graphical user interfaces that involves finite state machines. And if we had visual ways of showing those machines and allowing someone to edit those machines graphically, that could be useful even to experts, right? And related to that, there's an idea from a paper. This is a WIS 2014 paper by Steve Oney and his co-authors. It shows a very interesting way of displaying a finite state machine. So here I've drawn a finite state machine with 4 states, and the edges show transitions, and each transition in this particular example, it causes certain variables to be assigned certain values. So that's sort of a side detail that's not essential to the idea. What is interesting is that Steve Oney takes these states and then he displays them as blocks in a single row, okay? And because they're in a single row, then you have space below them to show all sorts of information about each state. You could show, for example, a list of instructions associated with each state. And the transitions between states could be triggered by an input event like a mouse clicking on something. So I think it'd be interesting to take this very novel idea of layout and applying that to a system where you have bidirectional updating, where on the right, maybe you have this graphical view of a state machine, and on the left, you have source code, and the 2 sides will update each other. A fourth idea for future work would be for us to say, there's no single graphical representation that's going to be perfect for everyone. So let's build an IDE that allows the programmer to have any visual representation they want for any portion of code, okay? So if I sketch that out, imagine you have a program with a whole bunch of lines of code. Maybe there's one part of the code that you want to show using a sort of data flow diagram or a bolt style representation, right? Maybe that's appropriate for this part of the code, and you can have bidirectional updating. Maybe there's another part of the code that you want to show in a different way. Maybe this part of the code defines part of the GUI, and if you change the GUI, the code gets updated, and vice versa. Another part might define part of a 3D scene. Another part might correspond to some abstract data structure, right? So imagine a GUI where you could take different sections of code and map them bidirectionally to different visual representations. I think this is a very interesting and promising direction for future work. And in fact, current IDEs already do this to some extent. Current IDEs allow us to import different types of assets or resources and then operate on them in the code. But what they don't currently have is this bidirectional updating. And another thing they don't have is that they don't make it easy for a programmer to add new representations. But maybe future IDEs could do that. Maybe they can make it very easy to define some new representation and then reuse it in future code projects. Another idea for future work could be, in all the examples I showed you, where there's programming by demonstration or programming by example, the visual representation might be very useful even to an expert because it allows us to directly manipulate the output. But none of the examples I showed you were Turing complete on this side. They are only Turing complete by virtue of the source code. So for example, in the example with the Sketch and Sketch, by editing the source code, we can define any algorithm. The source code, the textual representation is Turing complete, but the graphical output is not. Okay. And if we built this type of system with multiple visual representations, the system would be Turing complete by virtue of the textual input. But an interesting direction for future work would be try to come up with some visual representation, a purely visual representation that allows us to define things like conditional branching and manipulation of arrays, and allow Turing complete programming just through the visual representation. Okay, so that's my future direction number 5. And maybe 5.1 could be, can we make this work for pen input and maybe leverage some of the advantages of pen input with the sort of creative, informal aspect of it and leveraging of fine motor control of the hand. So this is a more vague idea, but maybe you're familiar with the text editor called Emacs, or another editor is a VI. These editors are famous for being very, very programmable. So a question you could think about related to Emacs is, what would be the equivalent of Emacs with pen input? So with Emacs, we have text input and we can program it to do anything. Can we imagine the same type of thing, but with pen input? How would you program things using pen input? Okay, so how are we doing for time? I think I've filled almost an hour, and it'd be good to have some time for questions. So let's see. I can turn off my screen sharing for now.
Mm-hmm. Yeah. Thank you very much, Michael. And it's really an inspiring talk. And I learned a lot. And not only from the technical part, but also like the way you say that when you see the confusions, then there's opportunities. I really appreciate that. Yeah. Okay, so we collect a lot of questions from different channels from Chinese audience, and then I will read them one by one. So first one is can visual programming support pixel level rendering, such as volume visualization, point-based visualization? More generally, is visual programming still limited by perception?
Okay, interesting. So for volume rendering, I have seen examples of systems where for example, if a user wants to define a shader, there are user interfaces for defining shaders visually. And that there's commercial products that do that. For example, in Unity and probably in Unreal Engine, there's ways to define shaders graphically. I've also seen academic papers that have various visual interfaces for defining what are they called, the transfer functions. I can't think of examples off the top of my head. I can sort of picture one or two examples, and if we did some searching, we could find examples. So yes, it is possible to do that. Pixel level rendering, well, there's a funny thing that you can do in Scratch. In Scratch, it's actually possible to draw individual pixels, and Scratch is not really designed for that, so it's quite awkward to do, but it is possible to do. And we could imagine modifying Scratch to make it easier to do that. And then another question I think was, is visual programming limited by our perceptual ability? And yeah, that's true. There are examples of visual programs that have lots and lots of crisscrossing lines, and it can be very hard to follow where one line goes to another block if there's lots and lots of lines all over the place. So it seems to me that a way to reduce that problem is to have the ability to define subroutines and abstractions and take certain blocks and put them inside meta blocks so that we can hide certain details. And it also seems to me that maybe by designing hybrid languages, we could mix the use of curved edges with blocks like the type of blocks we see in Scratch, and maybe we could reduce the problem of having something that's very visually complicated.
Yeah, okay, thank you. And the second question is that visual interface enables direct creation of visualization and lower the coding barrier. Yet under the scenario of visualization authoring, another challenge is for inexperienced users to design engaging, memorable, understandable VIS. What more features in this system do you think can somehow elevate this problem?
It's an interesting question. I don't have a good answer, but it reminds me that there are people working on things like data comics.
Benjamin, I think. Yeah.
Oh, yeah. Let's see. For example, Benjamin Bach, for example, and his co-authors have written various papers about data comics. So data comics can be sort of naturally drawn using pen input, and that's a way to make things more engaging. I don't know if there's any work on data comics that are interactive. So maybe interactive stories or narrative presentations of data. Maybe that could be a direction for future work.
Yeah. Okay. Yeah. The next question is that they say many of the visual programming work is done by industry, and what are the differences and advantages between academia and industry doing the visual programming?
What are the advantages of, sorry, what was the last sentence?
I mean, I think they just want to ask the differences between the academic and industry doing the visual programming.
Well, I guess in industry, maybe it's common that you have a visual programming language for a very specific purpose. You want to make it easy for your users to use one particular program. And so you're not necessarily interested in theoretical questions like, is the language Turing complete? You just want it to do some specific set of functions. But personally, I've been sort of confused and then interested in this idea of Turing completeness, and how is it that we can get the full potential advantage of these things. And so, yeah, I guess as researchers, we have the luxury that we can spend more time thinking more abstractly, and maybe some of our ideas are not really that good, but we only understand that after we've made some prototypes and really push things to the limit, that we understand, okay, this idea in theory works well, but then there's some problems that I didn't anticipate, I didn't expect. Whereas I think in industry, you don't usually have the time to try those things out, and you have to focus on something that is much more likely to succeed.
Okay, and yeah, so more things, and how to solve the problem of visual programming that is complicated by complex game design. Probably they want to see when people want to design games, and how to use the visual programming to design that.
Yeah. Actually, games are a very interesting application, because modern games are very complicated. You have lots of models, lots of animation. You have AI to control the behavior of non-player characters. You want the story to be interesting. And the people who make games, often I think they work very hard, and they're also very creative, but they have to be very practical. So I think that in the larger game companies, they will make tools that they use internally. The tools might be very good for solving certain kinds of problems. And I think a lot of the recent innovation in visual programming has come probably from the game industry. So if you look at things like Unity or Unreal Engine, maybe that's where there's been more innovation recently in visual programming and sort of visual ways of doing things. So for example, Bolt, I showed you Bolt. Bolt, as it happens, was developed by a tiny team of people here in Montreal, in my city. And then Unity decided to buy it. And I found it very interesting that in Bolt, you can define loops. But I don't think Bolt was the first language to do that. I suspect there are other languages that did it before. And I tried to find historically which was the first language to do it. I couldn't. So maybe that's because in industry, ideas might get copied or improved by people, and there's not necessarily a record of papers describing the history of those ideas. So I guess the question was, how can visual programming be used to make games more easily? I'm not sure. I think making games it's a very interesting application domain. It's very complicated. There are lots of different things that could be done visually. And the people who make games are doing their best to come up with the best tools to make those games.
Yeah, that's it. And the next question is that, how do you evaluate the effectiveness of a visual programming language? Are there any general rules or methods?
Yes, there are. There are survey papers that describe different criteria that can be used to compare and evaluate visual programming languages. So there's a few that are cited in our paper from last year. Let's see if maybe I can find an example quickly. There's one written by Ko. Oh, here it is. maybe I can paste this reference into the Zoom chat window. Yeah, so that paper, in the title, it talks about end user software engineering. So the objective of end user software engineering is very similar to visual programming. The idea is that we want to make it easier for people to customize code. And if I remember correctly, in that article, this article is cited many times. It's got to be cited more than 100 times at least. I think in that article, they mentioned Turing completeness and passing, and they say Turing completeness is not really a very interesting criterion. And they present other criteria to compare languages, if I remember correctly. So just those criteria could be used to evaluate languages analytically, but you could also evaluate them with user studies. And you could, for example, you could compare two different languages in a study where you have people try them out. They try to program something using two or more different languages, and then you observe what kinds of problems do they have. You can ask them questions about how they found each of the languages. You can measure the time it takes for them to do to make different programs in those languages. But I think those types of evaluations are challenging too, because there's potentially many features that you'd want to add to a language to make it comparable to something else. Like maybe you want to add support for subroutines and comments, and maybe even object-oriented programming. And there's a lot of work that you'd have to do to make it really comparable in a fair way to some traditional language. So yeah, but anyways, I guess there are those two big approaches. One is analytical, where you analyze the different features and criteria, and the second is evaluated with users.
Yeah, I think it's really, that's two approaches. Okay, the next question is that how to get a balance between powerful flexibility and usability, especially for non-programmers of hybrid graphical textual programming.
I guess it would be to minimize the number of instructions that you offer them. So if they don't need to use loops, don't give them loops. If there's only a tiny number of instructions, give them only those. Another way that you can help beginner programmers or beginner users is you can have a tutorial. So the first time they try the system, there's a tutorial that steps them through the process of making a small program. And I've seen this in more and more systems recently, not just programming systems, but other systems where the first time you log in or the first time you run it, not only does it explain to you step by step how to do something, but it asks you to do a few steps. So it'll tell you drag and drop from here to there. Now connect this to that, and then it explains the output. And by taking you by the hand and stepping you through the process, it's like having someone getting you to do some simple tasks so that you learn the basic concepts.
Yeah, I think it's also quite useful for the visualization designs.
Yeah.
And the next question is that the process of visual programming seems to be a little bit similar with like interactive AI. Has it been applied in interactive AI yet, or is it a topic that was working on?
I don't know if it's been applied. Is it worth working on? Probably, yeah.
Yeah, probably.
Yeah, I have very little knowledge of AI, but there's probably opportunities there to combine ideas from AI with ideas in visual programming or other more intelligent types of programming.
Yeah, I also think so. Yes. And the next question is that what scenario in visual programming more requires the GUI GUI completeness? For instance, it is hard to imagine why we need subroutines or conditional branches when constructing visualizations.
Well, I guess if you want to make a program that's long, then there's going to be a greater probability that you'll start repeating sets of instructions, right? And then it's very useful to be able to define subroutines so that you don't have repeated pieces of code. Why would you want conditional branching? Well, maybe you want the visualization to update in response to certain input events, depending on the type of data that the person has clicked on. So maybe if they click on one type of element you know, X should happen. If they click on a different type of element, then some other thing should happen. If you don't offer conditional branching, then there's going to be some algorithms or some things that the user won't be able to do. And maybe that's okay if there's just a limited set of things that you want the user to be able to do. But if you want the full power of computation, then you have to give them a Turing-complete language. So there's a trade-off, really, and there's a trade-off. You can give more flexibility, but there's also more opportunity for error and confusion. It's more difficult to learn.
Okay, I think these are all the questions I received. I think the audience really think a lot, and you inspire them a lot to get diverse questions. So
well,
yeah. So
thank you very much. I really enjoyed this. This is very stimulating for me. So
yeah.
here there's a 12-hour difference between Beijing and Montreal.
Mm-hmm.
So we've been very busy at home because we moved recently. So I actually woke up around 2:30 a.m. this morning to work on my slides, and yeah, I'm very awake because I had a lot of caffeine.
Okay.
So I enjoyed this very much.
Thank you very much for this very good effort, and it's really and there's a lot of audience account at the peak time. We have 2,400 something like people in the same time to watch this. So yeah, really, yeah, it make a really good impact. And so we have the last task, announce the next time speech. So can everyone see my slides? So the next speaker is Michael Glacier from University of Wisconsin Madison. And his talk is about interpreting embeddings with comparison. And the time is the 21st October. Please note that it's in the morning, 9 to 10, 30. So, and so I think for today, and thank you very much, Michael. And yeah, it's really great opportunities for learn this visual, the openness, these ideas, and hope you can come to China in a very near future, and we can discuss face to face. Mm-hmm.
Great. Well, thank you so much.
Yeah. Okay. Thank you. So probably you need to take a rest. Okay. Thank you, and thank you very much for all the audience and the volunteers. Thank you. Bye.
Bye.
Mm.